Good evening, and welcome to the next installment of the SLAC Public Lectures. I'm really glad to see such a great turnout for this talk, which, well, it's about the life and death of the universe, so I'm glad you folks are interested in that. I'd like to apologize to the people who were in the overflow room today. Our auditorium did not do well in the strong rains a few weeks ago. So that's why we're in this smaller space. So please excuse us, but I think we'll have it refurbished in time for the next public lecture 2 months from now. So tonight we have a real treat. We have Eli Rykoff, who is an astronomy staff member with the Kavli Institute for Particle Astrophysics and Cosmology at Stanford and here at SLAC. Eli got his PhD from the University of Michigan and working on large-scale surveys of the sky, and that's been his expertise for many years. He was a postdoctoral fellow at UC Santa Barbara. He spent a year and a half at Lawrence Berkeley Laboratory working with Saul Perlmutter, one of the people who won the Nobel Prize for the discovery of the accelerating expansion of the universe. Now he's come here to SLAC to work on the LSST project, which you will talk about. He's very interested in the shapes of galaxies, their form and their color. And tonight he will explain to you what looking at galaxies can tell us about the past and the future of the universe. So Eli, thank you very much. Thank you, Mike.
So thank you very much for having me. My name's Eli Rykoff, and I've been here. Michael's intro didn't maybe make it clear. I've been at SLAC now for 5 years. I just got my lapel pin just this week, and I forgot to bring it and wear it. So, yes, they give you a lapel pin if you've been here 5 years. I'm here to talk about galaxy clusters and the life and death of the universe. And although I do work on LSST, I also work on the Dark Energy Survey. And LSST is in the future and DES is today. So you'll be seeing a lot more pictures from DES than LSST. But let's get started right at the beginning. Get right into the thick of things. So the universe began in a hot Big Bang singularity, and space-time has been expanding ever since. And that first beginning is this period of inflation, which we call it, which lasted a fraction of a second. I don't want to get into inflation. That's a whole talk in itself. And then the cosmic microwave background, which I'll talk about in some little bit more detail, about 400,000 years later. And then this structure and all the gas evolved into the first stars after a couple 100 million years. And finally to today, almost 14 billion years later, we have stars, galaxies, clusters of galaxies, and people. And I'm going to tell you where galaxy clusters come in and tell us about this part and moving forward. So moving to the cosmic microwave background. So several 50, 60 years ago, looking out at the night sky with radio telescopes, they noticed that there was this little hum in the microwave at about 2.7 Kelvin, this cold glow coming, and it was the same in all directions. And so we say the universe is isotropic and homogeneous. It is quite smooth on large scales, and it is the same in all directions. But this is what it looks like at first, but if you zoom in and you have the sensitivity to look at fluctuations, this is 1 part in 100,000 from the Planck satellite, which is up now, or I think it might be taking data. There's little hot and cold spots, but these are only 1 part in 100,000. And this is the initial fluctuations. This is the initial changes in density that were imprinted at the beginning of the universe. And somehow, we got from there all the way to what we see today. And clearly, we are not uniform at 1 part in 100,000 today. So I'll be showing about how galaxy clusters tell us about that. And to answer the big questions about how we got from here to here and where we're going in the future. So one of the backgrounds that I have been talking about is, we got from there to here, but the universe is expanding. And Edwin Hubble noticed that what he called nebulae, what they called nebulae, but what we call galaxies today, that were further away, were moving faster. And this is the original 1929 Hubble expansion plot. And he said, okay, if the things that are moving, that are farther away are moving faster, then the universe must be expanding. And that was a pretty big deal. And then moving forward to 1999, it was discovered that the expansion of the universe was expanding even faster. It's speeding up. And this is using type 1a supernovae, but this is one of the big plots from Saul Perlmutter's 1999 paper, which allowed him to share the Nobel Prize, which was quite fun. Here's a picture of him enjoying the win, and you can see here Josh Myers right here, who's in the back of the room right now. He'll be helping answer questions. He was a grad student working for Saul at the time, and it was quite startling that morning. My alarm goes 6 in the morning or whatever, and top story on the news, the Nobel Prize in Physics was awarded today, and it goes to Saul Perlmutter and other people for the accelerating expansion of the universe. And what? Okay, but it's really amazing to see what this is LBL, what a national lab and Berkeley can do at the drop of a hat if someone wins a Nobel Prize. And there's seminars and champagne that appear out of nowhere, as well as big posters, big everything. It's all ready to go. Also discovering the fluctuations in the cosmic microwave background was a big deal. So what makes up the universe? This is a slight detour from that whole history. But I'll be talking about ordinary matter, which includes all of the stuff that makes stars, makes gas. There's a bunch of dark matter, and I'll show how that works, and then dark energy. And one of the mysterious things is that the ordinary matter, about 4 or 5% of the universe, is just a tiny fraction. Most of it we don't know about. So what is dark matter that makes up most of the universe? We call it dark because it neither absorbs nor emits light. So that's what it is, dark. And cosmologically, we call it cold dark matter. And it behaves like a physicist's ideal substance. It's wonderful. It's cold. It's slow-moving. It's non-relativistic. Only gravity. No messy gas physics. All of that hard gas physics is gone. It's just gravity pulling it together. So basically, it's like working in the proverbial frictionless vacuum that physics professors love to talk about. And the last SLAC public lecture from Tom Schutt, which many of you may have attended, about looking for dark matter and detecting it. And here's a nice little simulation. Though in these simulations, you might see all of these are little dark matter particles, and they look like they're glowing. Of course, they're not. The dark matter is itself dark. But when we display it for simulation purposes, we're just plotting brighter places where the density is greater. And then The other main constituent of the universe we call dark energy. It acts like a negative pressure accelerating the expansion of the universe. We don't know what it is. It's called dark energy, apparently, because if you call it dark energy, then it's more likely to get the interest of funders who want to fund energy research. So the simplest model of dark energy is what we call the cosmological constant lambda. And this becomes the lambda CDM universe. You put a cosmological constant with cold dark matter, and we have our so-called concordance cosmology. Everything that we observed so far in all of these surveys is consistent with this lambda CDM concordance model. But we haven't gotten sensitive enough to see if dark energy evolves with time. And this is one of the big questions that we hope to be able to answer. Basically, I'm a observational cosmologist. I make the measurements, and then we hand them to the theorists who come up with more and more exotic answers to how the universe goes with that. But again, everything looks like lambda CDM. So how exactly does this work? And for all of our measurements, we start with simulations because we're comparing to simulations. And we only have one universe that we have here. But in simulations, we can have many universes, and we can play around with different models and everything. So we have only one universe we can look at. So in this, I have two different universes. They start with the same initial conditions, we say. And we put dark matter and dark energy, and we have the equations of gravity, which pull all these together. We have the expansion of space-time, and we just let it go. And for the beginning, they look kind of the same, but you can see the dense parts are getting denser. And by this point, you can see in this universe, which has more matter, there are more nodes, more filaments, and the voids are deeper than here. So this is the fundamental observation that we're working with, is that if you have different constituents of the universe, then the large-scale structure evolves differently over time. And if we tell if our universe looks more like this or more like this, then we can see what the universe is made of. And we do this. I'll show you by looking at galaxy clusters. So here's another image of one of these. This is a beautiful image. Most of these videos and images come from Ralph Kaler, who works here at CAIPAC and does these wonderful visualizations. In this cosmic web, you can see nodes, you can see filaments, you can see voids, and you see these at all scales. If you zoom in, it's kind of a fractal structure. You can see within the nodes, you see other filaments and all of this. It's like really depends on the amount of dark energy and clumpiness. Now I've shown this, and this is all dark matter, but does the universe really look like this? And here's another great video. On the left side will be simulation. On the right side, observation from Sloan Digital Sky Survey, the BOSS survey. So on the right side, these are places where there are galaxies. On the left side, it's populating galaxies into this dark matter structure. And you tell me which side is really simulation and which is observation. So they both have the same structure. They both have the same nodes and filaments and all of that, and it's zooming out. And basically, this is just an example of how our universe actually does look like this stretched out in the way we have in our dark matter models. So looking back at the cosmic web, I want to just zoom in on this node to define a couple things. So this is just a zoom in from that previous slide. And what we call here, this big puffy thing, is a dark matter halo. There's little subhalos inside. And we call them halos because they're big and puffy and broad, and they're around all of the structure. But the halo is the essential part of the nodes of the dark matter that make cluster cosmology possible. And the measurement that we make is what we call the halo mass function. So we need to count and weigh dark matter halos as a function of time. So here's another simulation. Now, hopefully this isn't too much going on, but I'll run through it a couple of times. On the left, we have another one of these simulations. Now, little circles are coming on to show where the densest parts are. These are the halos that we're counting. On the right is a plot, number of halos as a function of mass. And I don't know if I can, nope. I don't think I can drive this. That's a shame. I can't pause it when it's in presenter mode. So over time, you can see at the high mass end, at first there's no high mass halos, and then there's more and more. And over time, this function evolves from basically no structure to the structure that we see today. And so the essential problem that we're trying to solve is to make this measurement and count the halos as a function of mass over as far back in time as we can. So what we need to know is, where are they on the sky, their position? How far away are they, their distance? And then we need to weigh the halos. How massive are they? And then we compare our observations to the model predictions, and that tells us what the universe is made of based on the different simulations. But the big problem is that dark matter is invisible. It neither absorbs nor emits light. So where are they on the sky? So going back to this image of the halo, at the center of each of these halos or subhalos is a tiny galaxy or cluster of galaxies. Now, you often see these simulations which show like big galaxies in here, but it's actually not like that. The galaxies are really small compared to the size of the halo, which are very puffed up. But what do the galaxies look like? As an example from galaxies, the Hubble 2 elliptical galaxies, which are redder, and spiral galaxies, which are bluer. And this is, if you want to look at pretty pictures of galaxies, check out Galaxy Zoo. What I'm most interested in are these red elliptical galaxies. And Tolstoy said, happy are all alike. Every unhappy family is unhappy in its own way. But the galaxies and clusters are really happy families of elliptical galaxies. They really all look alike. For these elliptical galaxies, star formation ended billions of years ago, and they just have these old stars that are just fading away over time. There's no new star formation, and they all look alike. And so what we end up is at the center of these biggest of these nodes are galaxy clusters. So finally, I have a picture of a galaxy cluster. Galaxy clusters are clusters of galaxies. And if you look, you can see these red galaxies here. I've highlighted, these are the brightest in this cluster called Abell 69. But there's actually more fainter ones here. And there's more members here. And you can see that they all have similar colors. And we call them red, even though they're kind of yellow. That's because they are redder than the other galaxies. But I'll talk a little bit more. I don't want to talk about color theory too much. But one of the problems that we have is that our eyes all see things differently than our telescopes do. And then you project it on the monitor, and you project it up here. And it goes through a transformation each time, so don't trust your eyes. Bigger clusters are bigger in all respects, and bigger clusters have more members, and you can count the members, and we call that richness. A richer cluster has more members, more gold galaxies, I guess you could say. And we can have richness as a proxy for mass. You can count the galaxies, and even though the galaxies are just a small fraction, 5% of the mass of the cluster, more galaxies equals more mass. And the other thing to know about galaxy clusters is that they are the largest bound objects in the universe. And one of the fun things when you sit down and write a cluster paper is to come up with a new way of phrasing this exact same thing. So these are quotes from some recent papers that I've been on or written. Clusters of galaxies are the largest bound objects in the universe. The galaxy clusters are the most massive of these bound structures. Galaxy clusters represent the most massive gravitationally bound structures in the universe. It goes on and on. Every one of the papers has a line that has to be slightly different. It's very tedious. But that's the lesson of where these galaxy clusters are. They're the center of the biggest nodes in the cosmic web. And I showed an image before of a cluster, and I highlighted where the red galaxies are. But here is a Hubble image from a distant cluster made by Josh Myers, who's there and back. He shows up twice in this talk. Thank you, Josh. And I'm going to play this animation, and it's going to reassemble all of the galaxies. And all the red galaxies go up here, and all the blue galaxies come up here, and they've been sorted by what we call a color magnitude diagram. But red is up, blue is down. This is all the galaxies in the field. These are bright foreground galaxies. These are all cluster members that are along the red sequence. So this red sequence, they stand out. And so this is one of the key things in detecting galaxy clusters. And here is the blue cloud. But you can see there's a pretty good separation between the red sequence and the blue cloud. So the way we look for clusters is we look for groups of these galaxies that are of about the same color. And what does that color mean? Here's a little aside about astronomy filters. So this is from the Dark Energy Survey. Our filters are G, stands for green, R for red, I for infrared, Z for, it's Z, right? And Y is, it's next to Z. I really don't know where the Z name came from. But the visible spectrum is right here. This is the visible spectrum that you can see, which doesn't even go through all of our so-called R band. Most of what we're looking at in our surveys, in these optical surveys, is in the very near infrared. But astronomically, we don't call this infrared. We call this optical because with an infrared telescope, you need to keep it cold. You have all sorts of other problems. And you can't use regular CCDs like you have in digital cameras. So here's our filters. But every color image that I show you is a composite of some of these bands, and none of it is the colors that we can see with our eyes. So even our basic, with DES, like our basic color reconstruction combines the G, the R, and the I band. But most of that is coming from the infrared where our eyes can't see. So keep in mind that every color image that I show you, not just in the simulations, but in the observations, is kind of a lie in that way. I mean, it's a false color image. These are all, but they're very useful for seeing what's going on. Now, the other thing about galaxy clusters is that they don't just have galaxies, they have X-rays. And clusters are filled with hot plasma emitting X-rays. But even this is only 15% of the mass of the cluster. The rest is dark matter. And if you go and you look here, this is the same cluster as before, and now I've superimposed the X-ray hot plasma over the galaxies. But the dark matter extent goes much further out. The dark matter halo goes much further out than we can effectively detect the X-rays. And dark matter, which makes up the rest of the mass of the cluster, is extremely important. Galaxies and clusters would fly apart without dark matter. The X-ray gas would boil away. It would just evaporate. And this was first discovered by Fritz Zwicky in the 30s about galaxy clusters. And here he is in a classic picture of him. I don't know what he's talking about. And for individual galaxies, that they would fly apart without dark matter, this was discovered by Vera Rubin, who recently passed away in December. And many people, including me, feel it is an injustice that she never won the Nobel Prize for her work, and now she never will. But she still had a wonderful career, and we thank her. So here is a simulation, again, from the group here, of a cluster with no dark matter. So holding together this cluster, these are all the yellowish galaxies here. And we'll just play, and you just take away the dark matter, and what happens? And all of these galaxies just fly apart. They become unbound. So it is the dark matter that's binding these together, but the galaxies tell us where that dark matter is. So how do we find these clusters? Well, we turn to optical sky surveys. And 3 surveys that I'll be mentioning. First is the Sloan Digital Sky Survey, 2-meter telescope with a 2 cubic gigaparsec, or 80 billion cubic light years, for what I would call cosmology quality cluster finding. This survey is completed, and this has been hugely influential for all of survey cosmology and astrophysics. Astounding publication to dollar ratio. The Dark Energy Survey, which I work on right now, it's a 4-meter telescope with 100,000 plus clusters. And then in the future, the Large Synoptic Survey Telescope, or LSST, an 8-meter telescope, 80 cubic gigaparsec volume, hundreds of thousands of clusters. So Dark Energy Survey it's the dark energy camera on the Blanco telescope in Chile. It's a 570 megapixel camera. International collaboration of hundreds of astrophysicists here, UK, Spain, Germany, Australia, Brazil, Switzerland. I have a colleague from Brazil here today. And here is a picture of the telescope, and here is a picture of the camera. It's a big camera, and the CCDs look kind of bluish because of the anti-reflective coating. And we're currently completing the 4th year of our 5-year mission. Now, DS has a very big field of view, so it's very efficient. Here's a pretty image of a cluster at redshift 0.4, and I'll talk a little bit about what that means in a moment. But here are you can see the yellowish, reddish galaxies. These are cluster members. But this is just a little stamp. This is 5 arc minutes by 5 arc minutes. Now we zoom out to something about the size of the moon. And the cluster is here, buried in the middle, and all of the structure around it. But even this is just a small fraction of what we see with one pointing per band. You have to image it multiple times to get the color image. But the clusters themselves are just these small little things buried in here, which we have to pick out. And it's not hard to pick them out because their colors stand out so well. So then finally, the LSST. It's a 10 square degree field of view, so a few times bigger than DES. A 3 gigapixel camera being built right here at SLAC. This is one of the big things that SLAC is doing over the next several years is building the LSST camera and image the entire visible sky in every 3 to 4 days, and DES equivalent every couple of months. So we're spending 5 years on this DES survey and pouring our lifeblood into it, and then LSST is just going to obsolete that after a couple months. That's progress. And here is a beautiful simulated image. And 20 terabytes of data per night for 10 years. So we use these surveys and we look for the reddish galaxies to find out where they are. But how far away are they? So now I have to say something about the redshifting universe. Well, light is a wave, and as the universe expands, light gets stretched. So here's our short wavelength light, and long wavelength light is red. And so here is let's take our Blanco telescope for the dark energy survey. And we have a galaxy here that's close by. Its light will be whatever color it is. As it gets further away, it gets redder. And I put a little fake red filter on this, and it gets further away, it gets redder still. So for the same galaxy, the farther away it is, the redder it will look because of the redshifting, because of the space-time itself is stretching and is stretching out those photons. The wavelength of light is expanding. And so here is pictures of some DES clusters that I've sampled. And you can see the yellowish going to reddish galaxies in them. And a little question for the audience. Which cluster is closer, this one or this one? This one? And this one's farther away. So this redshift parameter Z goes from 0.3 up to 0.87 in this sample of images. And there, just like that, you can tell how far away a cluster is. It's actually not that hard once you get the knack for it. And you can, with enough practice, you can look at a picture if you know what bands it was taken in and approximate how far away the cluster is. And if you can do it with your eye, you can do it very efficiently with the machine. And so, we write programs to do this for us. We do not scan each of these clusters individually by hand and look at the color and try to figure out how far it is. So we know where they are. We know how far away they are. And the next part we need is how massive are they? And so here we turn to gravitational lensing. So I've taken, here's our telescope, here's a foreground galaxy in this case, and here's a background galaxy. And the light is emitted like this. But the thing is that if this is massive enough, then it will actually distort space-time, and gravity will bend the light, act like a lens. And so when it bends the light like this, it'll look to us like the background galaxy is here. Because the light came like this, but we look, and the background galaxy is moved. And it could look also, if it's aligned properly, the background galaxy is over here as well, because the light took 2 paths around. And that forms something that we call an Einstein ring. This is strong lensing. This is a real image from the Hubble Space Telescope of a background, a foreground. This red galaxy is in the foreground. This blue galaxy is in the background. And it's just aligned. And you can see the whole ring as the light travels multiple paths all around. And I actually have a demo of this. So some years ago, it worked, hey. Some years ago, when I was a postdoc at UC Santa Barbara, the iPhone, Apple announced that you could start writing apps for the iPhone. And I thought, that's pretty cool. And my office mate at the time was Phil Marshall, who is he's here at SLAC now. He was at Santa Barbara then, and he was a strong lensing expert. And I said, Phil, can you help me with the math on the strong lensing while I put together a cute little app to see what lensing would look like on the iPhone. And this app is called GravLens 3, and it starts with a faint blue galaxy, and you put a little bright foreground galaxy, and it creates a little Einstein ring like we have. And we can move it around and create some little shear profile, and you can create these arcs, and you can do all these fun things. And if you look at a library of strong lenses, you can recreate many of them right here in the app. Let me bring up an image of the Hubble Ultra Deep Field. So here is the Hubble Ultra Deep Field, which I'll use as an example of a background field, which none of us actually have because we don't have these big space telescopes spending a ton of time. But this is not typical for DES background galaxies. And we can put a foreground galaxy, but as an example, I just want to highlight this little galaxy pair right here. And you can see it's kind of roundish and pointed up. I'm going to add a foreground galaxy, and you can see now it gets stretched. Even if it isn't totally distorted by the lens, it gets stretched a little bit. And if I make this bigger and more massive, it gets stretched more. So the more massive this is, the more stretching you have. And the way we use gravitational lensing to weigh the clusters is by looking at the stretching of the background galaxies. And these stretches are actually very, very small, but they are coherent. You can see not just in this strong lensing regime, as we call it, outside the stretches are aligned along a tangent. We can also do a little bit more fun stuff. I can also lens you fine folks. Let's see if this works. There, let's see. Come on. There we go. Oh, it's going a little slow today. If you put it on your phone, it'll be liquid smooth, but it's deciding it's not going to do that very well. But here's what you all look like behind a massive foreground cluster galaxy. So let's see. Does that work? Yes. So there's an app for that, GravLens 3, available on the App Store if you are interested. And if you're interested in doing citizen science with lenses, please visit spacewarps.org. This is Phil Marshall's modeling on computers has gotten a lot more sophisticated, and you can actually look at gravitational lenses and look at images of the sky and decide if they actually are real lenses. So going back to weighing clusters, what I showed in that demo, for weak lensing, the shapes of background galaxies are ever so slightly stretched by the foreground mass. And here, I've just zoomed in on that galaxy that I was highlighting. As you go to low foreground mass to high foreground mass, it gets more and more stretched. And the amount of stretching tells you the mass of the foreground cluster. And one of the big programs to really do this, I would say, right, is called Weighing the Giants, led by Stanford SLAC researchers. This was not done with DES. It was 51 clusters observed with large telescopes in Hawaii. And here is 4 views of one of the clusters. That's zoomed out, so you can't really see the optical image very well, but they've helpfully traced out where the red galaxies are, concentrated here at the center. This is where the lensing mass is. This is the background galaxies are ever so slightly stretched, which tells you that there's more mass here and it's centrally concentrated here. And then in X-rays, it looks like this. And you can also measure the X-ray properties, and you can compare all of these. And one of the things they did was compared to our estimates of what we call richness, a particular way of counting the red galaxies. And here is the X-ray gas mass, and here is the richness, and they are correlated. And here's the richness, and here's the total mass from weak lensing, and they're correlated. So again, the galaxies themselves that are used to compute the richness are just a very small fraction of the mass. But principle of bigger is bigger. More galaxies, more mass. And it actually correlates quite well. And this is what we do in our cosmology research. We use the clusters and we count their galaxies to tell us approximately how much mass. And then we use the lensing to calibrate that actual amount. But the problem with using the lensing is unless you have these very large telescopes in Hawaii, it becomes very difficult to do a whole bunch of clusters. And we can get tens, hundreds of thousands of clusters just by looking at the optical images. But for the lensing, you have to do the whole thing statistically. So looking at DES, where are the clusters? This is from the DES year one part of the footprint. And in here, we have the red are the dense spots, and the blue are the less dense spots. And this is at redshift 0.87, and I have a little animation here. So you can see from DES how the structure changes. Now this is just relative density, so this is not as high fidelity as looking at the nodes of filaments. And it changes over time, but you can see at certain places the structure grows and structure changes. And so this is how we're using the galaxies to trace where the mass is as a function of time, essentially. And then here is another image. This is a pretty image from our older science verification data, so a smaller footprint. And the color now is looking, instead of cluster density, this is looking at mass density. So this is basically the correlation of all of those shapes, those stretched shapes, to make a mass map, as we call it. And the red are the high mass regions, and the blue are the low mass regions. So these are the nodes. Here are the voids. And the circles are where all the clusters are. And so there's more clusters where there's more mass, and there's few clusters where there's little mass. So again, the mass from the weak lensing and the mass in the universe from the dark matter correlates very well with where the clusters are. And I don't have any exciting results to show you since we're not done with our analysis yet from DES. But we basically, again, we take the number of clusters per richness per redshift distance. This is we combine it with the weak lensing mass calibration, and we compare this to predicted halo mass function. And then we can constrain here, this is from a simulation, the total mass in the universe and the clumpiness of the universe. And one of the other things that I haven't talked much about, we can also use clusters here to actually test general relativity. If things go off the rails compared to our other probes, then one of the things that the growth of structure is sensitive to is general relativity consistent with the universe on the largest scales. And again, so far the answer is yes. There's been no deviations that we can see. So going back to our largest bound objects in the universe, these clusters that I've been talking about, once in a cluster, always in a cluster. And dark energy itself is space-time is expanding, and there's more dark energy being created. But once something is gravitationally bound. Once our solar system or anything bigger is bound, we say it decouples from the Hubble flow. It is no longer getting accelerated away from itself. And so these things are bound together, but what happens to the clusters in the far future? So this is the cheerful part of the talk. So I'm going to say a little bit about the sun and the solar system, a little digression, the local group, and finally the far future and island universes. So the sun itself, pulling way back closer to home, the evolution of stars is driven by gravity pulling in. Gravity is really incredible. And nuclear energy and thermal pressure pushing out. So you have gravity pushing in, thermal pressure pushing out. And it's in a delicate balance. And this changes over time. So as the sun ages, it gets brighter, hotter, and larger. In about 1 billion years, the sun will be 10% brighter than it is today. This will create a moist greenhouse effect. Will basically look like Venus. Evaporation of the oceans, wet stratosphere, rapid loss of water from the upper atmosphere, and a runaway greenhouse effect. In about 3 billion years, the sun will be 40% brighter, and this will be the runaway greenhouse effect with the evaporation of the oceans, heating of the surface melts the crust, and so we have, our lava. And finally, we have a red giant, and here's a cute little animation from ESO of the sun expanding into a red giant and what happens to the Earth. So it's getting bigger, and the Earth is getting cooked. But remember, the oceans are long gone by the time it gets to this point. And so we either have to push the Earth out or do something else. And oh dear, the camera took it too. So that's the solar system. But what can we see from the solar system? Well, the biggest galaxy in the sky is the Andromeda galaxy, and it's part of what we call the local group. Local group of galaxies is the Milky Way, the Magellanic Clouds, which you can see from the southern hemisphere, Andromeda, M33, and other smaller galaxies. And we're all gravitationally bound. And people have done some simulations showing what will happen with the Milky Way and Andromeda over, here's 500 million years, 1 billion years in the future. Now remember, the sun's warming up at this point, and the Earth is not so happy. By the time this all rolls around, the Earth is going to be cooked unless we can move it or move ourselves. But it's still a pretty image. And here, the galaxies are going to come together, and stars are going to get stripped off and fly away with these tidal tails. And 4.5 billion years in the future, we're going to have a second pass and then merge together into one galaxy that will look probably like an elliptical galaxy. So here's a nice little artist rendition from NASA of what the night sky will look like now if you're a professional astrophotographer. In 2 billion years, as these galaxies are coming together, we're all getting closer. It gets very pretty. But of course, at this point, we're not going to be standing on the Earth with these pretty mountains and looking at the scene. But there will be a big elliptical galaxy, directly in our sky, which will be kind of cool. But what happens to the future of structure? That's our local group, and it merges together. But we can go further forward. And using the standard cosmological model, we roll the clock forward. As I said, objects that are bound now will continue to be gravitationally bound. This includes our local group. But objects outside, including our neighbor Virgo cluster, which is nearest big galaxy cluster, will be accelerated away. So it's a little bye-bye to them. And so here is a simulation that a friend of mine and former colleague, he left for Silicon Valley, if you can believe it, did of looking forward in the future. So this is still the past. This A parameter is 1 today, and now we're moving to the future. And here is, it's a halo, and it just basically looks, again, it continues on like it is with these little subhalos slowly merging in. But so you have everything merges together into one little ball. But hopefully we can see this. So here is if you're an omniscient observer. You can see everything. You're godlike. And you look today, and you can see the structure of all of the dark matter, the filaments. We run 100 billion years into the future, and if you're standing outside the universe, which we can't do, then it would look much the same, only a little bit denser clumps because everything is merged together. The problem is that space-time itself is expanding. And so in 10 billion years, you can zoom in here, and you can see some neighbors, and maybe one neighbor. In 90 billion years, you're alone. You can't see anything. So the cosmology of the future is really kind of lonely. We're in a lucky time now that we can do this, because the cosmic microwave background is too cold. It's too faint to see. You wouldn't ever measure it, and the wavelength is too long. Other galaxies and clusters is too faint, too redshifted to see. In 100 billion years, the wavelength would be longer than, wavelength of light will be bigger than the Earth. So you wouldn't think to look out. You would see everything in our local group, and you wouldn't see any other galaxies or any clusters or any distant quasars or anything. We also can infer the history of the universe by looking at the elemental abundance from the Big Bang. It's all been reprocessed. It's all gone through multiple stars at this point in the far future. So every group, every cluster is the end point. This is its own island universe. And here's a little picture. It's a Moana wallpaper. And many stars have lifetimes well beyond this age. There will be stars in the universe. There will be the possibility of having, planets around, red stars and people on them. But if there were cosmologists, one of the strange things is if you go way back in time, a few billion years ago, you wouldn't know to look for dark energy because its effects hadn't really happened yet. And if you go far in the future, the universe is so dominated by dark energy that you wouldn't notice it either. You would have your own little universe, and you would think it was all matter. And you would go back to looking what we used to call the Einstein de Sitter model. It would be just a 100% matter universe with nothing else in it. And it's an interesting thing to think about because you'd be totally wrong about what the universe is made of because you can't observe it because you're too far away. So does that give us any clue about what we're looking at today? I don't know. Those cosmologists of the future who talked about the multiverse would be kind of correct. So in summary, this is my last slide. Galaxy clusters tell us about dark matter, dark energy, and the clumpiness of the universe. DS and LSST, we're going to detect hundreds of thousands of cluster out to early epochs of cluster formation. And as the largest bound structures of the universe, which you might remember at the end of this talk, in the far future, each cluster becomes an island universe to observers within it. And that's kind of the end state until everything cools into the heat death of the universe at the end. So, thank you.